Hi, everyone. Got my little face in the corner today for your pleasure. I'm just kidding. Okay, so I said I was going to make a 10-minute domain thing. Remember what we said. What is domain? Just what can X equal? You state what it can, but really look at what it cannot be, and then it can equal everything else. So pause the video if you didn't get a chance to write this. I'm going right to questions, man. Okay, so find the domain for the following functions. Support your work algebraically or graphically. Write it in interval notation. So if you have or vertical asymptotes, that also affects things. Okay, so I don't want to go over this too long. I hope you have a little bit of a connection here that I cannot plug in -4. When I plug in -4, I get a square root of a negative, which does not graph in a real coordinate plane. I know it's an I number. Actually, it's square root of -1, which is I, but it doesn't graph. So in the real world, in a real coordinate plane, the domain is limited so that it's limited to what can be plugged in because it's real, not imaginary. I guess I was about to say something more there, but that wouldn't have made sense. The very first number we can plug in is -3. And then what I'm doing is, say you were just being a robot and you went to your graphing calculator. Well, you'd see this. -3 plus 3 is 0. Square root of 0 is 0. So that's our first input value that we can put in. And then what I could plug in is -2. I don't want to go into this too long. I said this -2 plus 3 is 1, square root of 1 is 1. And this would be the graph, just very similar to the one that we had in the notes earlier. So what does that make the domain? It makes every number starting at -3 often to infinity is what I can plug in. And if I did, I would still get valid, real output values. Okay, so that's what that means. What is the domain? So for square roots, you're limited. You must have square root of 0 or square root of a positive when you're looking at that. Oh my. Well, I hope you remembered. If you actually take a picture of this, I thought she had graphs posted for this. I believe it is that one down there. If you were a robot, I'm calling you a robot. If you're, I just got to look at the graphing calculator and get my answers. You'll see this. Okay, and at least you got to be able to analyze it. So I'm going to zoom back and so you can see both the equation and the graph. X minus 5. The graph does something weird at 1, 2, 3, 4, 5. And you better remember from your math, ooh, very threatening. You better remember from your math 3 days that that's where you get vertical asymptotes, the zeros of the denominators. So vertical asymptote, VA, is actually quite technically x equals 5. Wait, you just said x can't equal 5. That's the point of a vertical asymptote. The graph does not exist at this, and then something really strange happens approaching that 5 value from the left and the right. And then, oh, there's another thing. So for domain purposes, x cannot equal 5. I know I'm confusing you probably here. This is just the equation of a line. An equation of lines, x equals a number, are vertical lines. So all I'm giving you is the equation of this asymptote, which is going to be part of our test or quiz next week, which is 100% related to, you know, uh, a domain issue. Sorry, I was doing something. I can hardly do two things at once. And then we got this. Oh no. But we also have another issue. X has to be greater than or equal to 0 as well. And that is combined in this whole function altogether. Because I just said you cannot take the square root of a negative. So this has to be 0 or higher. So establishing the domain actually is thinking. And then look at what I have to do. The domain is starting at 0 to 5, but excluding 5 because 5 creates that undefined value in the denominator. So you're listing what the domain is in interval notation. I did that in the first one, right? Darn tootin'. Oh, and I missed that this was here. X equals 5 is a vertical asymptote. Look at the picture. That's why the picture just flat out stops here. That's because you cannot plug in any negatives and get any graph over here. So another way to look at the domain is, hey, the graph exists here. Then there seems to be an interruption, and the graph exists here. So therefore, the domain is what I just stated up there. So that's how you analyze a picture for the domain. Oh, and then there's the picture if you were going to be a robot and put it on the graphic calculator. Really would be mad if you put that square root on a graphing calculator. But what can I do? I can't do anything. Too many questions from Westberg. Let's move on. Not ripping on her. It's just we don't have the time in this shortened period. Okay, no. Even when we go ahead and graph rational functions in chapter 2, we're going to the calculator. Boom. So you go to the calculator. I have minimal knowledge of this stuff. So, oh, wait, this is weird. I see this. Okay, I kind of remember this from last year. I see this graph here. I see this do a little, like a little, oh, okay. Oh, I remember x cannot equal 0, and that creates a vertical asymptote. So vertical asymptote at x equals 0. That means x cannot equal 0 in the domain. They are 100% related. Oh, 1, 2, 3. Okay. So for domain purposes, I got it figured out. See, because I could see the graph exists here. Remember what I said, input, output. The input is x, and then apparently I do have an output. So since I have these outputs, I'm allowed to put the inputs in. That's the way to look at this. Same thing on this side. All these and then all this gives me input output. So when I look at this graph, all these x's exist except for the asymptote values. Those cannot be plugged in. So negative infinity to 0, parenthesis, because if you put a bracket there, you're saying x can equal 0. 0, comma to 3. Union that with 3 to infinity and beyond. I haven't said that all year long. Oh, and I forgot to finish my asymptotes. So looking at that picture, then, oh, okay, I get it from the picture. Now I see what's going on with the equation. X cannot equal 0 and x cannot equal 3 because that'd give me a 0 in the denominator. Oh, no. I think this is the best way to look at this. Oh, Mr. Samus is really messing with my mind. Well, look. This is actually showing you that the graph only exists from here to here. Wild, weird, wacky stuff. That looks like it's from negative 2 to 2. Well, look at the numerator. When I put 2 squared, that's 4. 4 minus 4 is 0. I can take the square root of 0 and get 0. Input, output. Same thing with negative 2. When I plug it in, I get 0. 0 over who cares is 0. So that's why those points exist there. And then when I plug in anything between negative 2 and 2, you get various negative values. So what I'm trying to get you to understand is the graph doesn't exist over here and over here because of this. Sure, x cannot equal 3, but x already cannot equal 3 up here. So it's already out of the domain because of the numerator. There are no vertical asymptotes because of this special scenario here where x cannot equal 3 anyway because of the numerator. So the domain, by looking at the picture, is brackets because I can plug in negative 2 to 2. That's how you look at a picture to determine what the domain is. I don't have the time. I guess we'll go ahead and just say, hey, say you did this in a graphing calculator. And I would always make my kids actually plug in points to analyze this. But, you know, your brain's fried and you're like, okay, I'm just going to look at the picture. Pachow. All right, well, the picture, well, look. I can plug in 4 and I get 0, square root of 0, 0, plus 5. So this is at 4, comma 5. I think that's 5. I don't have time to count. All right, but then what happens when I plug in 5, 6, 7, 8? Who do we appreciate? Those are all I numbers when I plug that in. That's why the domain goes this way. I can plug in 3, 2, 1, blast off, negative 1, because the graph exists there. So that's how you use a graph to do what is the domain. And yes, you can plug in 4. Now, back in the day, I would cover range as well in these questions, but I guess we'll do that later. Then this one, just analyze that you do have vertical asymptotes, and that is the interruption. So go ahead and plug that in your calculator, but then do understand plus or minus 2 don't work. They give you a 0 in the denominator. That's why you see these interruptions here. So the domain of this one is all real numbers except 2 and -2. Fine, I'll write it. Negative infinity to -2. Union that with, oh, I do have to do -2 to 2, because that's this little chunk in between. Union that with 2 to infinity and beyond. Oh no, I'm at 1018. What a liar and a bum I am. Okay, so hopefully I was right about continuity being a thing. Nice. Okay, so continuity is real easy. Is a graph continuous? Remember what I said? Function, not a function, domain, and what is the domain? And now continuous is the function continuous. Continuous, I don't have to pick up my pen. Not continuous, there's a little hole there that ends up being up here. Who cares? This is called a removable discontinuity, or sometimes called a patch. Because what I could do is patch that up and then it would become continuous. So that's why it's called a removable discontinuity. There really isn't a great difference between these two, and I don't want you to worry about it right now. So that's a removable discontinuity. Hey, what would you do if you were playing a game and you were running on this, or you're a skater? A little Sammy Samuels is a skater. Yes, I named her Sammy so I could call her Sammy Samuels. I call her Sammy Sammy. But anyway, you're on a skateboard. There's no time for this, Mr. S. You said 10-minute video. What do you have to do to get from here to here? You have to jump. How can we not remember that this is a jump discontinuity? All right, very simple. There's a big gap between these two pictures. And then when you got an asymptote, you got a infinite discontinuity. That's what those pictures had up there. We're at 1140. What a mean guy. Okay, go to your graphing calculator. This is a trick, though. Feel free to slow this down. This is actually a really mean thing. This is the classic hole that you got last year. Because when you go ahead and type this in the Y1 screen, you get this picture. But at 0, it's undefined. And that's what this is showing, but it just got cut off when how I shared this or tried to put this in the notes. So this is actually a removable discontinuity because it's a hole. That's like the toughest discontinuous question you can have. This is not, just like we told, no, these x's don't cancel. 6 over 5 equals 2 error. Vertical asymptote at x equals 2, that's an infinite discontinuity. So graph is discontinuous if there's interruptions in it. 1238, my bad, dogs, riff.